Okay, so let's talk a few minutes about the report that you wrote for this week, and then we'll look at the solution to the homework assignment, and then we'll go on to some other stuff. Okay, so assignment was to write a 2 to 3 page paper discussing the stack data structure in terms of how it works, what its 3 specific functions are, and how modern programming languages use a stack to implement recursion. Finally, give an example of a problem for which a stack is the right tool for the job. Okay, so starters, what is a stack?
A stack is a type of linked list that allows the user to manipulate data using those 3 different functions, which are pop, feed, and push,
Okay.
which means you can add an element to the top of a stack, remove it from the top of the stack, or look at the value at the top of the stack.
Okay. So how are stacks used to implement recursion in modern programming languages?
Every call to a function, you save on the stack the address of the previous function. So
Okay.
after you execute the function, you have in the stack the last address for the function that called the function that was being executed. So you can come back and keep executing whatever else it was.
Okay, so essentially there's a package that's created with all the stuff associated with a function, and that gets packed up and thrown onto the stack so that the next time you need to come back to it, because that has to wait for the next recursive call to finish. So eventually you come back, and when you're ready to do the next thing, you pop it off the stack, unpackage it, and pick up where you left off. Okay, so recursion is implemented in terms of a stack in modern languages by taking a method that is currently executing that then calls itself and says, okay, I need to put myself on hold, so throws itself on the stack to be popped off later. Okay, and then what about an example of a problem for which a stack is the right tool for the job besides recursion? But
We have a compiler that needs to compile a kind of language that have brackets, for example. You have to count the brackets. You can use a stack that keeps counting each opening bracket. So you push in the stack, and when you find a closing bracket, you pop, and you
okay, yep.
Find the end of file, and the stack is
At the end, it should be the empty stack.
Yeah.
Okay, that's a good one. So without actually, I mean, in that particular case, you don't care how many opening and closing brackets there are. You just want to make sure that there was a matching, a matching closing bracket for every opening bracket. So that works for the matching. Doesn't necessarily make sure they're in the right order, but still works for the matching. Okay, anything else? We can make it a quiz.
Please don't do that. I'm fried.
You're fried? From what?
Capstone.
Isn't Capstone a blow-off course? Really?
Yeah.
What do you do in that class?
A major project.
All right, fine, whatever. So let's go and look at the homework assignment then. Use your stack data structure for storing disk objects. Implement the game The Towers of Hanoi for 3 disks and 3 columns. As simulated at this website. We'll go there in a second. So I'll copy that. And just so I'm starting off with the right starting point of code, I'll do that. Your program should use the scanner class for asking the user which column they are taking the disk from and which column they are adding the disk to. It should also enforce the rule that a larger disk cannot be placed on top of a smaller disk. Your program should detect when the goal is accomplished and display how many moves it took the user to complete. Okay, so if we go to this site, we get to play the Towers of Hanoi game. Oh, my flash is out of date. Excellent. Okay, but generally speaking, with Towers of Hanoi, we have 3 different stacks. Actually, you can have more than 3 stacks in more advanced versions of it. But the goal is that typically you start off with 3 disks on the far left stack. And your goal is to get those 3 disks in the same order on the far right stack. But you can only move 1 disk at a time, and you can never put a larger disk on top of a smaller disk. So you need to make the moves in such a way that everything gets transported over there. All right, so we're going to implement that using the stack data structure that we wrote in the online lecture last week. So I'm going to take a gander at that while this guy's doing this thing. We'll start a new project then. All right, so we'll go through this here in a second. All right, so here's our example of Towers of Hanoi. Notice that by default we have a number of disks as 3, but in more advanced versions of the game you could add to your number of disks. And the goal is to get this entire stack over to the other side, so you might do something like this. All right, and we won the game. I took more moves because I screwed up in the middle. But in any case, that's the goal of the game. So I gave you a starting point, and let's see what this guy does currently. If we run this, it should just show us, I'm guessing, the starting game board. Okay. Now let's look at the different pieces of this, so I can bring myself up to speed on this. Okay, so we're going to create an instance of our Towers of Hanoi object. So here's Towers of Hanoi. What's Towers of Hanoi? It's going to be a collection of tower objects. So we have an array of tower objects we're going to create. What's a tower object? A tower is a collection of disk objects. So we have an array of disk objects. Well, what's a disk object? A disk object has a size, the size of the disk. So we'll see what we defaulted the sizes to, but the larger the size, the bigger the disk. So using this example, this would be a smaller size disk than this one, and so on and so forth. All right. So when we create a tower, we say the number of disks that should go into that tower. The tower starts off as an array of 3 disks. That's the maximum number of disks one of our towers can hold. If we're hard coding in that the game we're playing is a 3-disk game. We set the current size to 1. And we go through and we fill up the tower with actual disk objects. Okay, where the actual disk objects are created with that cur size. So that's creating a brand new tower. So we initialize a tower to be a tower with 3 disks of size 1 on the tower. And then we also have a method here that returns a disk array called getDisks. So Tower of Hanoi is going to control 3 towers. Here's the constructor for it. So we're going to create our array of towers called the towers. It's going to be 3 towers. We're going to put at bucket 0 a tower with 3 disks in it. Num disks is 3. All right. So that's our 3 disks, the starting point. Then we have a tower that has no disks in it and another tower that has no disks in it. Okay. So when we pass in 3 here, it'll make our array capable of having 3 disks. That's hard-coded in there. Current size is 1. We'll fill that guy up with 3 disks. In the end, cur size will be 3. Okay. Now, this get pad string, that's going to be dealing with the display method, which is kind of a headache for Towers of Hanoi. So back in driver, after we create our Tower of Hanoi, we're just calling towersofhanoi.display, which is just going to call this method and draw the pretty picture of stuff that likely by the time we're done isn't going to look perfect, but it will work. Okay. So by far with Towers of Hanoi, the worst part of it, writing it as a text-based game, is making the towers all look nice. Okay, so that's what this guy does to start off with, right? And what we're supposed to do is we're supposed to actually implement the Towers of Hanoi game using this as our base so that it'll ask us a question using the scanner class so that we can say we want to move something from this column to this column. And it'll pop the disk off the top of the stack, push it onto this stack. Okay, now getting back to our tower, we're calling a tower a collection of disks, as we currently have it written here, right? It's a collection of disks. If we think about the Towers of Hanoi game, if I reset this, aren't each of these actually a stack? This is a stack of disks, correct? I can pop a disk off of this stack and I can push it onto this stack. I could pop a disk off this stack, and I could push it onto this stack, so on and so forth. Okay? So, first thing we might look at doing is we might look at making our tower a stack. Now, we already have a stack data structure here. So, stack extends linked list. So we wrote linked list prior. And what does a stack do? Well, a stack gets initially instantiated as a empty list, empty linked list. We have the feature of pushing something onto the stack. That means adding it to the front of the list. We can pop something off the stack, that is removing it from the front of the list. And then we can peek, which allows us to just see the front of it. It doesn't actually remove it. All right. So if we want to make a stack, or if we want to make a tower act like a stack, we could tell it that it extends stack if we'd like, because we've already built in these features into our stack data structure. But as it's written right now, our stack works with ints. We need it to work with disks, right? All right. So rather than making this guy extend our existing stack, what we might choose to do is implement a simple linked list, because stacks really are the simplest form of a linked list, or substantially simpler than a general purpose linked list, right? We only need to worry about adding and removing from the front. That's it. Nothing else. All right. So we're going to say that a tower is actually a stack. So maybe a tower doesn't even keep track of an array of disks. Maybe it keeps track of a linked list of disks. Right? Okay. Well, what's a linked list of disks? Well, we have to have a head pointer. And a head pointer is going to point to the first node, in our case, a disk. The first disk, right? So we have these guys, so we're going to have a collection of these dudes. So we're going to say a tower is going to have a private disk head. We're going to have the ability to push, which adds something to the front. Correct? Now, a disk becomes our node. So a disk knows about the next disk. Correct? So we need to augment our disk data type here. Because as it's written right now, these guys just kind of sit out there. Now, we could go back and use our original linked list and modify what a node is. We can modify nodes such that nodes are now a thing for a disk. But I'm going to write this in terms of a disk at the high level. So we're going to say a disk has a size, but a disk also knows about the next disk. So a disk actually becomes a node in the stack. Okay? So we're also then going to have a method, public disk get next disk, that will return this dot next disk. All right, so all disks know about the disk that comes after them, and we'll go ahead and give a disk the ability to let us know about the disk that comes after them. We know that a disk doesn't need to know about the disk that comes after them internally, but in order for this to function as a stack, it does. All right, We also need to give it the ability to set the next disk. So we can pass in a disk to this guy, and this guy's next disk will become that disk. Make sense? All right, so essentially what we just did is we added a couple of features onto our disk object. Really, at this point, it's a disk data structure. To our disk data structure, such that it knows about the next disk. All right, so now we're back to tower. A tower is going to have a head node instead of an array of disks. The head node is our path to all the other nodes, or head disk is our path to all the other disks. So I'll go ahead, just so we create our errors, I'll go ahead and remove our array of disks. That way we get our errors down here. We no longer hard-code it to be of length 3, which is good, because that allows us now to expand our game similar to this guy, where we can have multiple starting disks if we chose. Okay, we don't have to hard-code the array. We can now just add 12 disks to it if we wanted to. All right, so we're no longer filling up this disk array. We are going to keep track of the current size for the number of disks. This guy is going to tell us how many disks we need to put into this list. So we're going to go through num disks number of times, and instead of filling the array up, we need to add these disks to this tower. That is, we need to push each disk onto this tower. That make sense? So if we're going to push disks, let's get back down to 3 here. If I want to build this tower right here, the very first disk I need to create is the biggest one, and I'll push it onto that tower. Then I need to create the second biggest one, and I'll push it onto that tower. Then I need to create the third biggest one, and I'll push it onto that tower. So we're going to push 3 times. Make sense? Now, if we go back to this, notice that cur size we use to dictate the size of the disk. So we really need cur size here to start off at 3. That make sense? We're going to start it off at 3 because we want to make the biggest disk first, then the second biggest, then the third biggest. So it's going to go from 3 to 2 to 1 for our disk sizes. So we'll start it off at 3. We're going to loop through num disk number of times. Each time through, we'll create a brand new disk. And what are we going to do with that disk? We're going to push it. So this guy is going to take a disk D as a parameter, our push method here. So remember, we're augmenting this guy to be a stack. And what does it mean to push something onto a tower? Well, it means if the head node points to nothing currently, so we'll even go ahead and just say head is equal to null in the constructor. If the head node currently points nowhere, which it will in the first disk, we'll just set head equal to the disk we're adding. So if head is equal to null, then head gets D. Otherwise, okay, if head already points to something, we want head to point to the new guy, and we want the new guy to point to the same thing head currently points to. So we'll say D dot set next disk to head. And then we'll say head dot, well, then we'll say head is equal to D. So we set D's next disk to head, so that D now points to the same place head currently points to. Then we updated head to now point to D. And that's adding front. Make sense? All right. So that's what it means to push something onto the stack. So what are we going to do here? We're going to call this dot push that disk. Yep, and then cur size needs to go down by 1 each time. We're going to start off at 3, go to 2, go to 1, because of the order we're actually pushing it onto the stack, as opposed to from the way this was initially implemented, we did it in a array type fashion, not taking advantage of stacks. Make sense? Okay. Now we're going to have to come back later and add a little something to this push. Because as of right now, push doesn't check those rules. It allows us to just go ahead and push anything on top of any other size disk. Where we need to enforce that you can't put a larger disk on top of a smaller disk. All right, that makes sense? In fact, we can even do it now. So this guy is going to say what? If head is null, then we don't need to worry about the rule. There's nothing there. Otherwise, if there is something there, we need to make sure that the disk we're trying to add is smaller than the disk that's currently at the top. So else, if d dot get size is less than head dot get size, as long as that's true, we'll go ahead and let them push it on there. And as far as right now goes, well, otherwise it just won't work. The push didn't happen. We won't give them any error message or anything like that. Do I want to give them an error message just for now? Fine. Illegal move. So this is another output stream called system.err. So it's a parallel output stream to system.out, but it actually prints out in Eclipse in red. It's more of an interesting thing than anything else. Go ahead.
In the constructor, the current size should start with the number of disks size, right? Not if you want.
Oh, if I wanted to, if that's correct. If I want it to be generic, yep. So this should be num disks. This will work if we're doing 3 disks, but if I want this to be generic, where I can create a tower of any size disks, then I want this to start off at num disks. Okay, so this is push, and we'll throw a little error here if we have an issue. Now, towers also need to be able to pop. And we're going to have this guy return a disk. Okay. Do any rules need to be followed if you are popping? No, but I'm just popping it off the stack. If I'm looking at this, do I have to follow any rule here when I'm just popping this guy off?
No.
Okay, but what you were getting at is we got to make sure we're not empty, right? So we can't pop anything off a stack that has nothing in it.
Well, you can't pop the last one either, but that's not part of the rules anyway. So.
What do you mean pop the last one?
Like.
This guy here?
Yeah.
Well, right, but pop has nothing to do, when you call pop, it has nothing to do with the disk.
That's
Yeah, we're popping the stack and just whatever's on top pops off. All right, so we need to ask ourselves in pop, well, ultimately, we're always going to return head, correct? Well, potentially. But as of right now, what we want to ultimately return is head. But before we return it, we need to doctor the rest of the thing up to make sure the things point to what they're supposed to point to, correct? So, could use peak to check to see if it's null. Are we going to need peak for any other reason in this one?
only if you check in the current last one, if you're checking the current size of, say, what's on tower 2, and one of them is on, there's one in each tower.
Okay. Well, I suppose for completeness, we can go ahead and implement peak. All peak's going to do is it's going to return the head of the stack. Not remove it, just return it to let us look at it. So that's all peak is, very simple. Pop, we can say disk cur top is equal to this dot peak. If cur top is not equal to null, that is, there's actually something else there, then we're going to set head equal to head dot get next disk. And we've already preserved the guy we want to remove inside cur top, right? But we need to make cur top dot set next disk to null. We actually probably didn't need to do that because it'll probably get reset when we go to push it onto another stack. So we do that in our push here. We set the next disk to whatever it was.
Well, don't you need to call it from the top?
Well, we're not pushing yet. So these are two separate moves. I pop it,
Right.
and then the next thing I'll eventually do is push it someplace else. But I'm popping it from this tower, and then I'll push it onto this tower, or I'll pushing it onto this tower. So pop doesn't know where I'm pushing it yet. So we want to implement them as individual moves. So what I'm getting at here is this was probably unnecessary, but not wrong. I like to be explicit. So setting cur top's next disk to null is accurate. That is, we're about to pop this guy off the top, off the tower. He currently doesn't point anywhere. Okay, so we figure out what our cur top is. As long as it's something, we'll set it equal to the, we'll have head is equal to head's next disk. Move that down. Then we'll set cur top next disk to null. And ultimately we'll return cur top. And we can go ahead and do a little error message here. System.err.println nothing to pop. This guy must return a value. So in the event we peaked a null value, we'll just go ahead and return that null. We'll deal with that later, but that's what it'll end up doing. All right, so we'll peak at the top of the tower. As long as there was something there, we'll go ahead and set head equal to whatever head's next node is, because we've already preserved the top. Then we'll set cur top's next node to null. So this guy is just a loose disk. You know, when we have this guy dangling up in the air here, he's not pointing anywhere. And then we're going to return it. Okay? So that's this return cur top. If cur top was equal to null, that means we tried to pop something off an empty tower. Not going to work. Okay, so that's pop. Back in our constructor for tower, set the head to null. Cur size is our number of disks. We're going to build one with 3. This will spin through, and it'll push 3 separate disks with 3 separate sizes onto our tower. Make sense? All right. So we just converted this tower object into a stack-based data structure. Why didn't I have this guy extend stack? Values of disk. So the way we wrote our original stack was non-generic. It was okay. There's nothing wrong with that. But we wrote a non-generic stack to hold integers. Typically, if you're writing a generic data structure to be able to hold all sorts of different stuff, you would write a stack of objects. You know, that way you can, if you have a stack of objects, you can create a disk object and store it in there. You can have a node object and store it in there. Whatever you want, you can put into a stack of objects. But we hard-coded it as ints, and that's why we really couldn't use it. No biggie, we just converted our tower to a stack. Okay. After we finish this, I want to show you something called generics in Java. So somebody remind me about that. Would have made life a lot easier here. Okay. So this should fill up our tower. That's a pop. That's a peek. That's a push. And then get disks, we currently have returning an array of disks. Does get disks even make sense?
Because you're asking for all of them.
Say this again?
I said it doesn't because you're asking for all of them.
Well, with an array, I have a collection of disks. With a linked list, I have a head disk, which points to the next disk, which points to the next disk, which points to the next disk. Remember what we talked about 2 classes ago? I'm pretending that the video you watched, because I'm going back a year now. 2 classes ago, we dealt with this idea of arrays versus linked lists, where arrays are fast and memory inefficient, linked lists are slow and memory efficient. So this will return the entire collection of disks. Does having get disks even make sense right now? Probably not. Because really, the way I get disks from a tower is I pop them off the tower, right? And we might have to play around with this idea of having a temporary tower someplace else to push them onto. All right? So that's my tower. This is our disk. I think this is okay as of right now. So we use this toString method for our disks to represent them. So whatever the size is, we just double it. So if the size was a 1, it'll be 2 equal signs. If it was a 2, it'll be 4 equal signs, so on and so forth. That gives us our shape. Now back to Towers of Hanoi. Right off the bat, we're going to create an array of towers. Is that correct, or should we have a stack of towers? What's the right tool for the job? If we're building this, this is Towers of Hanoi. This whole thing here is Towers of Hanoi. Is this a stack of 3 towers, or is this a collection of 3 towers? Collection. So an array would make sense. Linked list could make sense. But given that we know we have 3 towers, does an array make the most sense here? It's the right tool for the job, right? If you wanted, and this does exist for Towers of Hanoi, you can have more than 3 towers. Then you might want to have it as a linked list, so you can have it pass. You could pass it an arbitrary number of towers, where your goal is to get everything from the first tower all the way to the last tower, and you had everything in between to work with. All right, but we're not going to deal with that. We have a collection of 3 towers. So we're going to keep this guy as an array because it's the right tool for the job. It's going to be a collection of 3 towers. The first tower will have 3 disks on it. The second tower will have no disks. Third tower will have no disks. All fine and dandy. This get pad string, and we might have to rewrite some of this. This is so we get the right spacing for the stuff when we're displaying it. You know, in fact, it what?
It worked.
Yeah, I know it worked, but I kind of might want to dump it. All right, well, let's walk through display. So display is going to put our base out there. So this is that first thing is this guy right here, this little crossbar, right, that we're going to put our towers on top of, or our disks on top of. We have an array called cur disks that we're going to hope to get from our get disks. It's not going to fly, right? So this line becomes obsolete, doesn't work anymore. because of the nature of our tower. If this is our tower object just has a head that points to the next guy, which points to the next guy. So if I want to display this method, or this tower, how might I do it? We're drawing pictures here.
You know the size of the tower, you create one. So you can create an attribute and a getter for it.
Okay. Well, do I know the size of the tower?
Yes. The number of discs, you know.
A tower, I don't think, tells us how many discs are in it.
Yeah, it's in the constructor.
Well, we knew about it back here in the constructor.
Yeah.
But down here in display, do we know about it?
No, I'm
yeah,
saying
once
to
you
create
get the
an
one.
attribute and a public getter in the tower class.
Okay, in the tower class.
Yep. Once you.
With the number of the size, the number of the discs.
Okay, so you want a tower to keep track of the number of discs. Yeah. Okay, so you want to have we'll make it private again, int num discs, and then this dot num discs is equal to num discs.
You have to control it on the top and push.
What do you mean I already used num discs?
So, never mind.
This is a local variable, and we're gonna set the global variable this dot num disc. So this guy up here, we're gonna set him equal to whatever the number of discs are for this. When we pop something, only when we successfully pop it, we need to say num discs minus minus. We don't want to subtract from it when there was nothing to pop. When we add something, let's do it in two places. Num discs plus plus there, also num discs plus plus here. So in both places where our tower expands, but not when we have an error. Make sense? So it's either the empty tower, now we have a num disc is 1, or, so it would be a 0, now it'll become a 1. Or it goes up by 1, whatever it was. So we augmented that. So now a tower becomes aware of the number of disks. And we probably want to then expose it. Public int get num disks. All right. So now a tower can report to us how many disks it currently has. Could be handy for us. All right. So back to Towers of Hanoi. There's our base. Num disks is going to be the tower dot get num disks. That's going to tell us how many disks there are there, right? Okay. And we're still, this guy's looking fishy to me here. This cur disks array here. We might have to use another structure to make this work. So I'm going to cur spaces is just going to be equal to num disks minus 1, and that goes with our padding and how far something needs to move over. So that's just our formatting stuff. So is this indent thing for each disk that's in the current tower. Now, one thing I want us to consider here is we know that from the current tower, I can pop num disks number of times, right? Okay, that's a fact that we can work with here. So, what's the tower's dot length? That's 3, correct? This dot the towers, that's this guy up here, that's our array of 3 towers. So what does this loop say? This loop says for each tower that we have, we'll go ahead and grab our current disks into this array called cur disks. We have a problem. Say this again. We got rid of get disks, so this guy's dead. But we also have an issue now. A tower is a stack.
Right.
Do I know how many disks are in that stack?
Numbers.
Now a tower can tell us how many disks are in it. If I know how many disks I need to store, can I put it into an array? I absolutely could. Right? Could we teach our tower to give us its collection as an array? For this is displaying purposes, right? We know that a tower might look like this. This is head, which points to this guy, which points to this guy. If I want to get this into an array, I'm going to get this guy, but I don't want to pop this guy. I'm going to create an array that is num disks in size. And I'm going to walk through my stack, copying the disks over. Make sense? Copying, not removing them. So we go back to tower. I'll just do it up here. Public disk array get disks. Say this again.
Can you use this method for search?
To search it?
Yeah.
Why would you want to search?
For example, for search in this tab. Not for for example, just.
I get what you're saying. If you needed to search through a stack,
Yeah.
could you convert it into an array? Well, that's essentially what this says, is convert stack to array and then search through it. Yeah, there's not a good reason why you couldn't. So you'd have to come down to whether or not it's the right tool for the job. If the search is going through a lot of information and it needs to be fast, then yes. Typically, not always, but typically a stack would not be something you would think of as being searchable. That would be more of a list or maybe even a queue, but typically even not a queue. Stacks and queues become special purposes. But yeah, you certainly could. You certainly could. So I'm going to go ahead and I'm going to return an array of disks from getDisks here. And so I'm going to create a disk array, call it temp, and this guy's going to be a new disk array of what size? How many disks do I have to have in here? Num disks, number of disks. Right? So this dot num disks. Now I need to go through and I need to fill it. So for int I is equal to 0, I is less than this dot num disks I plus plus. That's the number of times I need to walk through my stack. I'm going to need to keep track of the current disk. So disk cur disk, we'll start that guy off at the head of the stack. And I'll say temp at bucket I gets the value of cur disk. Then cur disk is equal to cur disk dot get next disk. And then at the end, we'll return temp. All right. So getDisks does this. It creates a brand new array, a structure for holding this many disks. We create a pointer that points to the front of the stack, front of the linked list in this case. We go through, fill up our array, with the current disk we're pointing at, then make the current disk point to its own next disk, walking down the stack. So cur disk initially pointed here, then it pointed here, then it pointed here. And for each of those, we copied it into the array. We did not remove it from the tower. So this is giving us the stack as an array. That's what getDisks does here. All right. So for each tower, We'll go to the current tower and get its disks as an array. We're going to go ahead and get bucket J. So this is for each disk in that tower. We'll print it out, or print it out here, depending on whether or not we needed a pad. And this is a tab, \T. So now they think this should work. Display method line 37. It did, oh, null pointer exception. It did not like when we I'm almost positive it's at this line, because we tried to, from an empty tower, we couldn't even get bucket 0. All right, so let's walk through this here. Initially, num disks is the number of disks in our very first tower, which first time through is going to be 3, right? Spacing is just for, an indent is just for display. So I'm just going to actually skip over that. For each of those 3 disks, we want to go through all the towers. That's what this says, is go through all the towers. We're going to go ahead and get the collection of disks from the current tower, the tower at bucket I, which will be 3. Temp will be equal to cur disks at bucket 0. Display it. Spin back up. I is now 1. Temp is equal to cur disk at 1. Cur disk at 2. It'll get our 3 disks. No harm, no foul. Display them. We hit the end of the for loop. We do our spacing crap. Spin back up. Now J is 2. So now we're at 0 to this dot the towers dot length, or now no, this is still 0. 0 to this dot the towers dot length, which is 3. So for each tower, go through and get the cur disks. So this is going to return for tower at bucket. Oh, we're only drawing the base. The way this is drawing it is it's doing this, actually it's doing this, then this, then this, instead of one tower at a time, which makes perfect sense. All right, so this going to num disks, this is telling us the number of disks in tower 0. I wonder if that's even like the correct way of doing it. Well, let's walk through it anyways. So number of disks in tower 0, which originally would be 3. We're going to go through each of those disks. That's the number of rows we're going to paint. Okay, so we're doing this as a row 1, row 2, row 3. Then, for each tower, we want to do row 0 for each tower. We'll get the disks for that tower, current tower we're looking at. We'll go ahead and get the disk at bucket J. Well, some of our towers aren't going to have a disk at bucket J, correct? So, well, I think this is supposed to cover it. So this asks if temp is not equal to null. So if there actually is a disk inside of cur disks, then do this. So our get disks must be broken compared to the previous get disks. Previous get disks would have returned an array of 0 elements. So I'm thinking it's dying right here. Cur disks at bucket J. just see. I bet you it dies at 38. 37 of display, which is right here. This dot, the towers at bucket I. Well, it's complaining that this is a null pointer.
Well, they say it's inside the get disk method. It's the null pointer.
Get disks at 27. Oh, because the last time through, when cur disk is when cur disk is the last disk. This dot num disks. Yeah, it's the very last time through where we're setting it. And the quick fix is throw an if statement here. So we know we need to get, let's just imagine this is 3 disks. We need to get 3 disks. So this is 0 to 3, so 0, 1, 2. We'll go ahead and get the first disk. Now cur disk points to its own next disk. So now it's pointing at disk 1. Spin back up, we'll get disk 1. Now cur disk is pointing to its next disk, which is disk 2. And disk 2 has no next disk.
We have to say.
Well, wait, hold on. That should work though. So the first time through, temp at bucket I is cur disk. Fine. Then cur disk points to the next disk. So now we're at this one. Second disk here. Spin back up. Temp at bucket I gets that disk. Then cur disk is equal to cur disk's next disk. This guy. Spin back up, set this guy to that. Then we're going to set cur disk equal to cur disk's next disk. This guy does have a next disk. It's null.
No,
That's, I mean, it shouldn't be a null pointer exception. Where does disk next disk? Well, one thing I'm going to add in here, I like to explicitly set things to null. So I'm going to say this dot next disk is equal to null. So when we first bring a disk into existence, its size will be whatever the size is, and it currently does not point to another disk. All right. Get next disk should return
I think there's exception, throw exception.
Well, yeah, but I mean, I'm wondering where the null pointer exception is. Get next disk is going to return a disk that is the next disk of the disk we just called. Back here in tower, we went through and we said, add this guy to the array, then set cur disk equal to his own next disk. Here. Add this guy to the array, then set cur disk equal to his own next disk. Add this guy to the array, then set cur disk equal to this guy's next disk, which is null, but it's perfectly legitimate to set cur disk equal to null. There's nothing illegal about that.
Why you don't put a system out print and see in which loop is throwing the exception?
Well, let's yeah, let's go into the debugger. Actually, a disk knows how to. Let's just print the disk. I'm going to put it up. Put it there. So there's the small discs. Why did it go through an extra time?
Because when you create the towers, one of them is zeros.
Just for the sake of argument here, I mean, the issue is, as we see how this is displaying, this is going to a row 4. You know, this guy down here, which says that there was more, that the initial call back here in Towers of Hanoi, num disks right here, is 4. It's at least bigger than 3. All right. So there's a problem. So we know that's an issue. So now we need to go back to our tower. When that first tower was being built, we passed in a 3 to it, right? So there's our 3. Oh, we set num disks to 3. Right there. Well, is that okay? It's not okay because we pushed them. We set it to 3, then it became 4, then it became 5, then it became 6. Yeah, so we're going to start num disks off at 0 because all towers start off empty. Then we start pushing crap onto the towers, and that's when they start getting stuff in them. This is what I get for changing something that was perfectly working into a stack. All right, so there's our 3 there. There's our initial tower, and then now we're dealing with a new problem. Okay, so let's get back. I don't need this guy now.
The problem now is because the array is empty. It's size 0.
Yeah, I'm trying to access bucket 0 of it. So that is this right here. So we're running into an error right here.
It's supposed to tower of the 3.
I mean, I guess we could just say if curdisks.length is greater than 0, then do this. Else temp is equal to null. That looks like garbage. It looked so pretty before. All right. Well, so at least the errors are out. So the error we were getting before is when we were trying to get from curdisk at bucket J. So now let's find out why it's not moving over now that we have this thing functional. So those bases get drawn on the 4th time through, right? Here's our base. So that's the very last time through. And our base is actually getting drawn in here. Yeah, there's our bases. So that part still looks fine. All right, so we're going to go for, this is our, well, initially, this is going to actually have to change later on. Because right now, this, as it's currently written, it assumes that we have a standard starting point for Towers of Hanoi, which will have num disks in the very first tower. as we move through the game, now tower 3 or tower at bucket 2 dictates the height of everything. And if we're taking the height off this guy, we're not going to do anything. All right, but let's get it at least displaying right the first time. All right, so j equals 0. J is less than the number of disks. We know that's 3. For this guy. Go through each tower. So we're at row 0 right now. We'll get the disks from the current tower, tower 0, which will be 3 disks. Its length is greater than 0. So we'll go ahead and get the very first disk. And then we'll display the very first disk. Then we're tabbing over. That's what the \T does. Spin back up. Now we're going to go to tower 2, or tower at bucket 1. Tower at bucket 1. We'll get the disks from there, which is going to be an empty array, right? So length is not greater than 0, so we'll set temp to null. If temp is null, we're going to just get a pad string to display. So it should display out to the right. Then another tab. Spin back up, get another empty array, do the tab string, or the length of the base string as spaces, tab over. We're done with this inner loop, kick it down a line. Okay. Spin back up. Now j is equal to 1. So we're at row 1. For each of the disks, we'll get the disk from our first tower. We'll get the second disk from that guy. And that guy has 3, so we're okay with that. So that's the disk at bucket 1. J is 1. Display it. Tab. Spin up. We'll get the disks from tower at bucket 1. He doesn't have a length greater than 0. So we'll display the padded string. Tab over. Do it again. Spin back up. So I think that we definitely are getting our tab pad strings. So this has the pad strings there. Why is all this stuff? Why is it displaying that 3 times? Num disks is going to be our 3 disks. That's 3 disks high. This guy is the which tower we're currently getting the thing from. So get us the first disk. This guy, display it. There isn't a disk at bucket 0 here. So just display the tab spaces. There isn't a disk here, display tab spaces. I think that's happening. Then we're kicking it down a line. So now we're here. This should be, I am interested in
J, not I.
no, I is the current tower.
I think that to get this method
Yeah, I think this guy must be building an array that we don't think it's building.
Yeah, before the method display was expecting an array of the size of disk, and each element should be null if there's not an element there. So if there's only 2 disks, the array should have the size of 3, and 1 element should be null.
Oh, got it. Okay, so back in tower, we need to make get disks work a little bit better. Num disks should not just be num disks. Num disk should be 3 if we're just going to make it work for this example, regardless of how many disks are actually in there. We'll go ahead and fill it up with yeah, well, we need to fill it up with nulls until we get down to
It's already null.
well, we're reading it from the top down. So if we have that tower that only has one disk in it, we're going to return an array that's null, null, this disk. Right? All right, so we need to build that array such that it's null, null, that disk. So we can fill it up with, so that's 3 minus 1 is 2. That's how many nulls. All right, so it would be something along these lines.
Yes, there is a print system that out of print. You're looking for a sign, the second row or row.
All right, I like to be explicit. Put the nulls in. So we're going to force nulls in there. This guy's not going to start off at that. It's going to start off at 3 minus this dot num disks to fill it.
There's a print.
Like that. Okay. Well, now we have it looking decent. We need to have this guy handle the problem of not getting the number of disks from the first tower. In fact, is there anything wrong with always assuming num disks is 3? Since we're already hard coding it.
No, you can get was the same that was before you create this method, because now the array of the get disk is always the right size.
Oh, so instead of getting num disks, we can say this dot get disks dot length, which is what we had there before. Because it'll always be that 3. So this is equivalent to just saying 3. Just looks more legit. Okay. So we should then, just to play around with this for a second, we should be able to take a I'm just going to make these public real quick, just so we can test our display method. That's the stupidest thing about this one, is the display method is by far the hardest part. So that displays the entire board. now we're going to take, actually, let's just do it in Towers of Hanoi. After we build our towers, we're going to say the towers at bucket 0 dot pop, the towers at bucket 1 dot push. So we'll go ahead and pop the first thing. We're going to do this move. Pop this, push this. So now our thing should look like that. Make sure our display method can accurately show that. And it can't. I hate our display method.
Hate is a very strong word. The equivalent is dislike, which is less strong.
I hate it. So now when we pop off the first one, let me just try this. I'm going to say the towers at bucket 0 dot pop. We won't do anything with it. Let's just remove that first guy. Oh, interesting. So let's go look at our pop method here. So we're going to get the cur top, which would be that small disk when we're popping off the first one. As long as it's not null, which it's not, we'll set head equal to the head's next disk. Then we set cur tops next disk to null. And we subtract the number of disks in here. Fair enough.
Oh, that's why it's displaying the 4 disc. I mean the second disc, because now that's the new top.
All right, but why didn't it display this disk?
Because you didn't ask about that disc.
Well, I'm still displaying the entire.
It didn't care.
There should be. That is the medium-sized disk, right?
Right.
Yeah. So we're missing the large one.
Right. I think your computer's saying you playing too many games.
Just for the sake of argument, when we pop let me just do this here real quick. I'm going to put that print statement back in here. Yeah, we don't have the big. Get the top. That's going to be the top of the stack. As long as it existed, we want head to point to whatever head currently points to, which should now point to the second guy in the stack. So this is cur top, this is now head. Then we're going to set cur top's next node, this guy, equal to nothing. And that's okay because head still points to this guy.
What was the second disk head?
Because I did it right here.
Oh, okay. Oh, God.
The num disks minus minus, subtract 1 from the number of disks in there. Fair enough, so now it should be 2. And then ultimately we'll return cur top.
So you don't need to add anything in there that shows the bottom one to whatever's under cur top? Because my assumption would be it's only returning cur top. I mean,
Well, this should only be returning cur top. This is our pop.
right.
So if our stack already looks like this guy points to this guy points to this guy.
Right.
So when I remove this and just make head point to this guy still points here. We didn't change that at all. I want to know what.
Yeah, but since you're only asking for now cur top, I don't think it cares about
Well, that's all pop is supposed to do. All pop is supposed to do is take one thing off.
Right.
So all I do is I call pop, and we literally throw it out.
Right. But it,
So in my little world here, I'm doing that. That's what should be left. I didn't put it anywhere else. I just popped it and left it. So we should now have a array of disks.
I think because they get when you build the photo, the last photo.
Yeah, realistically, we're about 5 minutes from me just erasing all this stuff and rewriting that in a better way. That's that's where we're sitting right now. But I want to check to see what. Disk array D is equal to the towers at bucket 0 dot get disks. All right, so this should give me, for that first tower, it should give me, well, I'm only doing it. It should give me a null and then 2 disks.
Yes. Yes, because the for load you just get it.
Yes, this is the problem.
The pop function, I think that the element after you were like the temper. If you go to the class tower, I think the problem is the 48 line, the line 48. It's.
oh, set next disk equals null. I
I
mean,
think that the current top it's pointing to where the new head is pointing to.
yeah. So the disk after cur top is now null. You just said it.
Well, clearly it looks like you're right. Let me just think through it. So here's a pointer, cur top. Cur top's going to point to the same place that this dot peak points to, which is just like saying return to head, return head. So this is the same thing as saying head. That's a synonym. Okay, so cur top is equal to head. They both point to the same place right now. But then I changed the value of head. I said head equal to head's next disk. So now head is a new value. That shouldn't have changed cur top.
No, it's a pointer to an object. So you are changing the pointer of the head and current top it's pointing to.
Itself.
We let's draw our picture here. Doesn't matter that they're not different sizes. So we have head. Head points here. Then we have cur top, which points to the same place that head points to. All right, that's the current setup at the beginning, right?
I'm thinking that cur top points to head, not to the same place that head is pointing.
Well, head's a pointer. So head holds the memory address of a disk. Cur disk now holds that same memory address. So both of these guys have a value that's a memory address. So if we say this is memory address 100, this is memory address 200, and this is memory address 300, the value of head is currently, oh, actually want to do it with the, it's currently 100. So when we set cur top equal to head, we set cur top equal to the same value that head is, which is 100. So they both point to the same place. Then, the very next line, where are we at here? Towers, pop.
There you go.
So, cur top is equal to head. As long as it's not null, which it's not, we're going to change the value of head to set head equal to whatever head's next disk is. So, this is head. This guy's next disk is this guy. So we should update head to point here. So head now has a value of 200. But that should not have an impact on cur top. Then we're setting cur top's next disk. So here's cur top. We're setting his next disk. Oh! Wait. No, I thought I had it solved. Don't. Okay.
You saying cur top get next disk, which should be equal to.
No, we're saying set next disk. So cur top set next disk is going to now make this guy point nowhere, which is okay because this guy pointed here, this guy pointed here. So cur top dot set next disk to null. Let's just make sure we wrote set next disk right. This dot next disk equals whatever disk we pass it. Fine. So we're going to set cur top's next disk equal to nothing. So now it no longer links to this guy. These two are no longer linked, which is okay because head still points to this guy. And this guy still points to this guy.
Yeah, but now that you're returning cur top, it's going to return null.
No, cur top I didn't set to null. I set cur top's next disk to null.
But you didn't reset cur top to be whatever head is now.
Who?
Cur top is not set to anything now.
Well, actually, this could be a problem right there.
That's what I'm saying. Cur top is not set to anything, so you can't return.
In the event of the null, well, I do have to return null. Actually, that probably wasn't a problem. Because I didn't make it an error. I just said nothing to pop and just returned the null value from cur top. Shouldn't have hurt anything. In our example here, cur top will point to that the small disk. So it's not going to be equal to null. So we're going to be inside of this if statement right here. And this if statement says make head point to head's next node. Make cur top's next node equal null. Subtract the number of disks this guy currently holds.
Oh, wait, so go back to your image, please. So here you got cur top equaling what used to be head. And now,
Head pointed here to begin with.
right, but when
So before we called pop,
hmm
this is what the world looked like before we called pop.
right. But now that you said curve top equal to head, and then you moved head down to the next node or next disk,
By setting cur top equal to head, I do this. I make them both point to the same place.
right, but now you move,
Then I said head equal to his own next node.
right, and then you moved what curve top was, so whatever was after curve top is now no. But you're trying to return curve top.
Well, cur top points to this guy.
Curve
This guy is a disk. This disk has a next node, a next disk that points here. I no longer need to point to him because I have a head that points to him.
But after you already cleared that out and you said, okay, now we're setting his next node to no, and then you're trying to return curve top. Hold on, wait, now you come confused. See, you should have never started over. I was on the roll, and then you started over.
They both point to the same place.
Mm-hmm.
Then I make head point to his own next node.
Right, which makes sense.
Fine.
But
Right now, this node points here. By setting it to null, all I do is make it no longer point here. I broke that connection.
But you don't need to return curve top because curve top is going to be what you just popped off.
But it's not popped yet. I need to return it to pop it. So I do need to return it here. Because if I'm popping from this particular stack, ultimately I'm returning this guy, which is cur top.
So when you're displaying it,
I'm not popping it during display. So what I do here inside of Towers of Hanoi, I pop it just arbitrarily after I construct my towers, just to see if my display method would still work.
right,
So I pop that guy off there. So basically I leave my tower looking like this, and I don't put this guy anywhere. So I'm starting with a perfectly good Towers of Hanoi board, and then just arbitrarily popping this guy off the board.
yeah,
So that's my new board. That's what my board. That's what my intent is, for my board to look like that when all is said and done.
right. But that's not what the code is doing.
Well, clearly.
I just want to say the problems come from the printing. I mean, there is nothing without into the copy.
Well, here I got the discs. So let me do this real quick. A quarter or something. You just take one and pay it next week or something. Okay, so let me not display it. I'll just have my Towers of Hanoi go in, build the towers, and then I'm arbitrarily displaying some stuff here. So that's the problem. Why doesn't this guy link to this guy? That link is getting broken. I wonder if it was ever set up.
It wasn't. That's what I'm trying to tell you.
So let me not pop.
Can you go to the picture, to the drawing?
Crack me up.
Yeah, I believe when you say that cool top received top, he's not pointing to 100. It's pointing to the address where head is pointing to. Okay, so head has an address, right?
Yep.
So it's not pointing directly to the 100 address. It's pointing to the head address. It's like the
Well, I get what you're saying. You're saying this lives somewhere in memory.
no, the arrow is wrong. It's not pointing directly to the 100.
Yeah, you're saying it's this.
Yeah.
It's not.
Yeah,
It's
kinda.
not the way it works.
Yeah, but that's the way you wrote it.
No.
No, no,
I do follow with what you're saying. I don't think that works. I mean, that's not how it works.
Well, because you said it instead of it being peak now, and I know it means the same thing, but
Oh, it does mean the same thing. We're getting the same result. Well, we are. Whether I say peak here or head here, we're getting the same bad result.
Yeah.
So those are synonyms for each other. We're not getting the right output.
Try
Kurt.
creating a new object here, like new disk
Okay.
instead of attributing the head down. Like Kurt talk receive new disk.
Well, actually, let's do this. This will be the better way to prove it. I'm just going to rename that to strings. That way, when we print, we can print out memory addresses.
Okay.
All right. So we're going to come into tower. Right after this line, let's go ahead and print out those two things. So we're going to do system.out.println head. And we're going to say system.out.println curtop. These should both print the same memory address because they both point to the same place. All right, so then let me not print here just so we don't muddy the waters with extra crap. Oh, I'm not popping. I'm never calling pop. There we go. All right, same memory address. These guys both point to the same exact place. So that should be evidence that it does do this. They're both pointing to the same place. Now, let's go through our changes and see what they're still pointing to after the changes. So inside of this, we're going to change head. So now head and curtop should be different values. Curtop should be what it used to be. It didn't change. But head should now be its own next node. Okay, different values, like they're supposed to be. And here, just to keep us sane, to make sure they didn't actually change somewhere in the middle, we'll print them out. We should have two that are the same, and then two that are different, with the second one being the same as the first two. Two are the same,
Oh, okay.
and then the second one the same as the first two.
Gotcha.
Okay?
Excuse me, I just want to say about the num disk when you make it like degrees minus minus because you did the if you get back to get disk.
Get disks.
Yes.
Where did I write that? Here it is.
I think the problem is coming from the photo, the first one. And disk 3 minus 1. I'd make it none.
Num disk minus this dot num disk.
Yeah, that's what make it none for the third one.
Instead of 3?
Oh yeah, because you got 3 disks in the
Yes,
stack.
it is. And when you bought one,
That's what I'm thinking he's saying.
you know, it's 3 minus 2.
Oh, so we didn't break the connection. We just filled our array wrong.
Exactly.
Okay. There's there's potentially some validity to that. Now, we didn't actually break something. We're just displaying it poorly.
And targeting.
Okay, so
I think you
if numDisk started off as 3,
you didn't need for the first row.
well, let's just walk through it. So if numDisk started off as 3, if I'm trying to get the disks from a full stack, this will be 3 minus 3, which is 0. So we won't actually go through this at all. Then we'll start I off at 0, go all the way up to 2, 0, 1, 2, and display them all. So this works for the full stack. When we subtract 1 from numDisk, now numDisk is 2. 3 minus 2 is 1. So we're going to go through here and we're going to fill up bucket 0 with a null.
Right.
Then we're going to go from I is equal to 1. I is less than 3. I plus plus.
2.
Actually, it'd be 2.
Oh. Oh. So this should just be 3. That's always 3. That's not going to change anything with our way we're currently writing this. So now I should be able to undo that. Should be able to go in here and let's take out these print statements. Oh, it's because it actually did work.
Yeah.
We just need to turn this back to toString. That way println knows how to print it. Okay. That's better. Which means now we should be able to go into Towers of Hanoi. I should be able to get rid of that. Then go into driver. We'll actually call it display. There we go. So pop the top one, leave us with that, which should then allow us to do something like this. So I'll pop the top one but push it onto the second stack. So this should now show us the second one with a single guy on it. I could pop from there again. We'll put it on the bucket 2, so now we should have one disk per. Spacing isn't working out so hot, but that's fine for right now. Okay, so it looks like our array of disks is now working, correct? All right, now the good news is that I've decided that where am I going here? Hate all of this.
All that work in time for nothing.
No, our array of disks works. We're able to get an array of disks. We're going to display this better, so it actually looks right. So I have 3 towers. All right, so initially my towers look like this, but they may look like that at some point. All right, what I want to do is I'm going to treat this as a game board. Okay, we're going to look at a 2-dimensional array. So I want to treat this as a game board. Now, it's not that important that our display works correctly. Let me actually think about this for a second. Before we do that, we'll go back to the version that worked. Doesn't look pretty, but it works. I'm ultimately going to make this look better using a 2-dimensional array. And we're going to just fill the grid up with our towers. That makes sense? It'll look better. For right now, we'll make this work. So now that we've gotten our display function working again, I no longer need this push and pop. Now we can go into our driver. Actually, we probably want to do it inside of Towers of Hanoi. Maybe put a public method in here called play. And the play method is going to create a scanner. All right. And just for right now, we're just going to say while true. We'll say system.out.println. Well, let's do print. Source. We need to import java.util for our scanner. So we'll say int source is equal to input dot next int Then we want the destination. We'll read in the destination. All right, and then we're going to say, we're not going to do error checking right this second, but we're going to say this dot the towers dot put, well actually the towers at bucket dest dot push this dot the towers at bucket source dot pop. All right, and then after we do that, we'll then say this dot display the board again. Okay. And we'll probably also, right at the beginning here, call this dot display to display the initial board. So inside of driver, we'll create our towers of Hanoi, and then we're going to play. First thing play does is show our initial board. Then it goes through this infinite loop that allows us to move stuff around. And I'm doing this as 0 index, so first tower is tower 0. So this is 0, this is 1, this is 2. Okay. And we can even label those if we wanted, but for right now we're not going to. So we'll run this. It's asking us for the source, so we're going to say the source is 0. The destination is 1. Display it again, it moved it over. Source is 0. Destination is 2. Moved it over. Source is 1. Destination is 2. Moved it over. Source is 0. Destination is 1. Moved it over. Source is 2. Destination is 0. Moved that over. Actually, we're kind of playing this crappy, but that's fine. So we're seeing that our mechanics work, right? Okay. All right. Now, every time we make a move, we need to count our number of moves, right? So int num moves. Start that off at 0.
Why? The lowest number is
Say this again.
why? The lowest number is equal to
Well, at the beginning, we haven't made any moves. So before, when we first start playing, we have not made any moves until it's asked us to make a move. So every single time we make a move, we're going to call this a move. We'll say num moves plus plus. Okay? Now, we only want to increase the number of moves if the move we just made was a legal move. Okay, so we'll deal with that here in a few minutes. We're going to take a break here in a minute. I just want to kind of get us to a stopping point. All right, so this is the move we intend. Right now, we're assuming that's a legal move. We make the move, then we add something to our moves. Every time we make a move, we must then check to see whether or not there is a winner. Right? So we might say, is there a winner? What does it mean for there to be a winner?
That
You
somebody
get the right, you make it
Tower 3 has what?
3 discs.
3 discs, right?
in order.
They would be in order if we enforce the rules.
Are we going to enforce?
Well, we actually already are enforcing the rules. We're not calling them on it. We're going to count every move. But for instance, if I go from 0 to 1, and then I go from 0 to 1 again, it doesn't work.
Oh yeah.
Okay, it still counted the move, but it didn't, because right now we're allowing it to count the move, but it didn't allow us to make the illegal move because we popped it. Yeah. Because we didn't detect it, we still popped this guy. We weren't allowed to push it, and then we just let it die. Okay, it went nowhere. So we lost puzzle pieces. All right, so we know what's going on there. All right, so what we need to do when we come back, and we'll be able to finish this up fairly quickly, is we need to check for a winner, so we know when everything's got all over there. And then when we make our move, we need to detect whether the move was legitimate. And if it wasn't, we need to make sure we push the disk back where we got it. Right?
Yeah.
If I try to push it onto the wrong stack, we need to be notified. Then we need to push it back where we got it so that we didn't destroy our game. All right? So let's take 10 minutes. We'll regroup now that we just got our display method working. Hopefully you see how easy the assignment actually was if display was working.
Oh my goodness.
All right, so I'll get this this video uploaded. So